Yes, upwind scheme possible, but at an awful price. To change the nature of your problem. To start now about a discussion for different diffusion mechanisms. Now remember, diffusion, if it's positive, we like it. It softens things down, smears out gradients. If it's negative, he blows things up. We don't like that. And the different types that we can physically talk about, physically and numerically. You of course have the viscous diffusion, then you have kinematic viscosity. You can talk about turbulent diffusion, and that's actually including a turbulence model, which then ends up in anti-viscosity. Then you also add viscosity into the problem, but you do it in a way that you have control. You know what this eddy viscosity is, and that he should represent the turbulent nature in the flow. Then what I call the artificial. So that's something that we have added on purpose. We choose a scheme that has some additional artificial diffusion built into it. And finally, the numerical ones that I say is negative. It's there inside your scheme, and it's hard to do anything about it. Of course, here it's in the example you saw, it evolved from the first order forward Euler step. So yes, you can do more advanced time stepping. The Runge-Kutta, Adams-Bashford, second order or something. Then he will be smaller, but he will still be there, and he will be negative. So here's a real pain. You can even talk about other diffusion mechanisms not listed here. We will see the effect of it later on. That is, if you have more than a one-dimensional flow, if it's a 2D or a 3D flow, and the flow direction is not aligned with your grid lines, then you can have a smearing effect of that as well. So we have additional diffusion mechanisms also. Now for a more heavy example. The Berger's equation. This is a model equation for the Navier-Stokes. Here it's a viscous transient Berger equation. You have the time term, and here a linear convection term. A is a positive constant, and yes, we also have the diffusion with us. So for this material here, you will see how you can achieve the modified equation after creating a numerical scheme of this Berger equation here. So here also I use the subscript for derivatives, and then we start out. Creating a forward time, but then here is a combination of central and first order upwind scheme. I have a parameter alpha, which is sort of a switch. If you say alpha is 0, then you get rid of this, and you are back with the second order accurate central space differencing for this convective term. Remember, it's only the convective term where you have a velocity in front that you can actually use this upwind scheme. Nothing to do with the viscous term. That's just a double derivative. You don't have any upwind direction here. You need a velocity in front before you can talk about upwind speed. If you choose alpha equals 1, well, then a little bit algebra, you will see this one will be the first order upwind scheme. And then of course you could choose alpha 1/2. Then you have 50% of each. That's a hybrid scheme. That's also possible. So here I have sort of taken both schemes into one. So it's a hybrid scheme, a mix. And now we see the modified equation for this one. So of course a little bit more to read here. Same goes here with the Taylor series, which we now have to insert into the schemes, and this is going to be messy, of course, but it's exactly the same as we did with the advection equation alone. And we end up with something like this. We get our original differential equation back. Thank you. It's consistent. When all these deltas tends towards 0, then you get rid of those. So this is now the truncation adduct. And also you can tell the order of this scheme is first order in time. In space, well, that's a question for this parameter alpha. If you choose alpha equal to be 0, then it's pure central scheme. It is gone. Then it's second order accurate. If you choose alpha different from 0, okay, and then it's first order accurate in space. Again, rearrange this equation. So I write it on this form, all the terms, and then equal to something that should be equal to 0. And now we start seeking the pure modified equation. Yep.
For hybrid scheme, would you always refer as the first order as soon as you have parts of it?
Yeah, even 1%, yeah, then it's down to first order, formally. In practice, I wouldn't worry too much about it, of course. Yeah, don't mention the war, or whatever you call it. Okay, seeking the modified equation. I want to keep the original terms, this one, and this one into my equation. I will not have this guy here. I want to get rid of him. So again, we have to construct some operators. And the first one, you take the original equation that you have, and then take the time derivative of him, multiply with minus delta t half. Yes, then you will get rid of this double time derivative. But when you do it, you give birth to a new term, and so on. So what we have in the end is something like this. So you can create a table, a large piece of paper, write all possible combinations of all time and space derivatives, and just write the coefficients here in the table. So the original equation was the coefficient 1, a, delta t, and so on. And first step was to get rid of him. Then we construct an operator, time derivative. So this term now becomes this one, so the sum will be 0 here. Sadly, then we give birth to a mix, gx, this one, which then we have to get rid of here, taking the x derivative of the original equation multiplied with plus a delta t half, and so on. And so you can continue as far as you want. No reason to overdo it, because we sort of know what we are aiming for in the end here. The question is, how many additional ux's do you get? So when you have too many derivatives, you don't get any ux's anymore, then you can stop. So here I went pretty far just to be sure. So you see, I'm very sure. Anyhow, we have almost the same answer as we had with the advection equation alone. We have just one additional term here. The viscosity has appeared as well, as it should in front of the double derivative. And now we can talk about stability. One stability criteria would simply be the square bracket must be positive. So this is also a sort of a stability investigation as well, finding this modified equation. And we have the same different diffusion mechanisms. The negative one, that's implied in the scheme, unavoidable, and negative, that's sad. And here, the positive term, if you have an alpha different from 0, if you use the upwind scheme, or part of it, then he will appear. But here also you see, if you use 1% of it, it doesn't really help much. if he's still big. And in practice, this can be very big. Of course, small enough delta T, then you could survive getting the overall viscosity positive. But remember, for real fluids, this is very, very small. Then this is going to be very, very small, and the A, that's the velocity in front of the convective term. He can be big, and then he's squared. Thank you very much. This can be a real pain, of course. Here we have the different diffusion terms. And then some discussion here. If we have a pure central space scheme, alpha is a 0, then we have to choose a delta T smaller than something with viscosity. And this is actually also one of the criteria you find in the Sola algorithm, because that one is based on pure central schemes. So you could try playing around with different Reynolds number for different flows there and see how small delta T has to be. It can be a real problem. Upstream, okay, it stabilizes, and if you look in sort of the worst case scenario, the viscosity is 0, then you're back to the advection equation. Then it goes without saying that yes, then you have to use the upwind scheme. Finally, if we have a mix, we have viscosity a little bit, and we choose more or less also the upwind scheme, and then we rewrite this square bracket, including all our diffusion mechanisms, by using this cell Reynolds number, sometimes also called a Peclet number, a local Reynolds number based on here it's just this reference velocity A, but a local length delta x for the cell. Then you can get it on this form. Now, as briefly mentioned, that yes, the cell Reynolds number, that's something that's going to give us some restrictions there. It has to be rather small, actually, especially if you don't have time in the problem. So that's a demand for delta x. Delta x has to be small enough so you resolve the physics in space. Goes without saying. But if this cell Reynolds number now is, say, a little bit big, maybe bigger than 2, for instance, and we choose upwind scheme, well, then we are actually doubling the viscosity. So if you think you're simulating air, you're not. You're simulating honey or something, very sticky fluid. So it's dangerous using this upwind scheme, of course it is. So that's something we have to keep in mind. It will be the discussion next week. We will start with, have a peek into the finite volume, the first one there. I think I put it up for you. Yes. So I'll go through this one next week, talk a little bit about finite volume, because the first examples he jump into is exactly what we have been struggling with now, the central versus upwind schemes. So this will be the topic then for next week. What I wanted to do now, before we stop today, was to dig a little bit further into this code here. This was now the advection equation, and here we ended with choice number 2, the first order upwind scheme, which then had a very strong smearing effect. You add a lot of viscosity into this problem. If we now try a hybrid scheme here, I choose 50% of each. That's an option. 4. So now I have chosen half is upwind, half is central. CFL number is fairly small, so it helps, but you can't, whatever you do, you can't really get it correct here. You have a more advanced scheme called Lax-Lendorf, where they actually introduce the double derivative into the scheme as well. So it's a higher order scheme, more advanced. And if we try this one, then that's choice 3. Yeah, still unstable, and it really doesn't help. You can use smaller delta T if you like, but no remedy at all. So the only way to do this correct was actually to solve it as a hyperbolic regression system, going more along the characteristics. That's the only way for a pure advection equation. Finally, we have something called implicit methods. Now if I choose an implicit here, just to show you, it doesn't even help. What is an implicit method? Implicit, then we are talking backward Euler. So for this scheme here, so implicit, for this equation here, 0 of ux equal to 0, the advection equation. How you write an explicit scheme? Well, then you write it on the form n plus 1 minus ujn divided by delta t. That's still a first order Euler step. But now you will take everything else, not as old values, but as new values, as unknown. So here it comes n plus 1. J plus 1 minus uj minus 1, n plus 1 divided by 2 times delta x equal to 0. That's fully implicit. And if you have the diffusion equation, sort of the same problem there, equals uxx, you will have the exact same formula there as well. N plus 1 minus ujn over delta t equals, and then on the other side, double derivative, j plus 1 minus 2 times center point plus j minus 1 over delta x squared. And all of these should be new, n plus 1 for all of them. So to use an implicit scheme, you have to solve a total equation system on each time step. Now we have to throw all our n plus 1 on one side, and you're not left with much on the other side actually here. You will be left with just a single un in both versions here. Now you could create a hybrid version. So if we now say multiplying this one with, what should we call it? 1 minus alpha, for instance. And then you write this one again, ujn, j plus 1 minus 2 times center point plus j minus 1 n over delta x squared, and now you just multiply him with an alpha. There you have a hybrid scheme. So if alpha equals 1, then you are back to the fully explicit scheme. Alpha is 0, it's fully implicit. Alpha is 1/2, it's a hybrid scheme, you have 50% of each. So yes, you can do this. And if we try it, you are in for some surprises here. I won't go through the stability analysis for fully implicit schemes. You can do it and you will see they are unconditionally stable. Fully implicit, you can do whatever you want. Delta t can be 1 million years, that's okay. And then you can find a steady state solution in one jump. Yes, that's possible. Actually, then what you're doing, if you do it like that, you're removing this one and you find the steady state solution. So that's by using a direct method. That's also possible. But using implicit methods for a transient problem, this is a danger. This is a real danger. Like this one, it's implicit, so I can choose any time step I like. Should be stable. If I now choose, let's see, delta t of 1. Yeah, it's stable. And I can choose a delta t of 2. So now I'm violating the CFL condition, but he is still stable. Still gives a stupid result, but he's stable. I don't have that many time steps here, do I? I don't. Let's see. Where's my time loop? Tmax should be 30. Okay. So let's have a time step of 10. He's stable, but the results is, I would call it highly questionable, to say the least. This was the advection problem. If we go back to the diffusion, should be here somewhere. Now where did we leave off there? We had a fully explicit scheme, and if we had the stability limit, this ratio R should be smaller than 1/2, then it was stable. So here it is stable, that should be okay. And if you go a little bit above, he will explode. That was what we saw. But now I can choose partly implicit scheme. If I choose number 2, and here I have an alpha set to be 0. Should have alpha equal 0.5. Then I take 50% of each. And now let's see what happens. The stability analysis now is a little bit more complex. So now it reads 2 times alpha minus 1 multiplied with r. Has to be smaller than 1/2. But alpha equals 1/2. That means this is going to be 0, no matter what delta t you pick. So these are unconditionally stable, no matter what. And yes, it is. So this will be quite okay. But now it's the same time step as we had with the explicit method. So let us increase it a little bit. Delta t is here. Increase him a factor of 100. And you see it's still stable. Now let's see how the solution looks. Whoops. Whoops. You see, he's totally crazy. In the end, he will find the steady state solution, yes. But no, you can't get the transient behavior correctly. He's totally crazy. So using a partial implicit scheme, you don't do it if you really want to have the correct time behavior. If I increase it even further, I can have a time step here of 1. It's still stable, but it looks really, really stupid. So no, this is not a good idea. We could increase it You do it a little bit better if you choose a pure scheme. Let's see, alpha, where was alpha? Here. Alpha is 0, then I think it's pure implicit. No, it's not. Yes, it is. Then he finds at least a more proper behavior. That's correct, but he doesn't get the right time. You see, he's extremely stable. Minus 2,500. Yes, that is smaller than 1/2. Very stable indeed. But the first time step is so big that you are actually quite close to the steady state. But according to the correct analytical solution, you are far from the right development. So very efficient to find the steady state, fair enough. But then I would suggest, if you're only interested in a steady state, don't use a transient code, use a steady state code. That will be the same. So using implicit schemes, I don't see the point. You have some negative behavior. It goes without saying, if you think about it, the time derivative, that was only first order accurate, either implicit or explicit. So an adder will be of order delta t. Choose a big delta t and you choose a big adder. Goes without saying. So if you want an accurate and implicit scheme, then it really has to be a fourth order Runge-Kutta or something. Or else you are dead before you begin. You're going to have a very big adder if you choose a very big delta t. So it's a bad idea in that respect. It's a bad idea when it comes to programming. For each time step you have to solve an entire equation system. That costs CPU. So why waste money and effort on something that calculates wrong anyway? So explicit schemes are frequently something that you would prefer above implicit schemes. The only thing that he has that is nice, it's unconditionally stable. Sometimes we really love that. And dangerously, the first codes that were sold, the first version of Fluent, you have several others as well. They typically used upwind schemes, implicit schemes, semi-implicit schemes, just to get things stable. And that meant whatever stupid things you entered into these codes, you got an answer. And the answer was 500% wrong, but you still got an answer. So then I actually would prefer that the code blew up in my face than giving me an answer which is rather hilarious. So they have been, of course, getting better now, these CFD codes, but some of them are still a little bit too robust, I think. They should blow up more often than they do. You will see that when you start playing around with these codes. We will play around with OpenFOAM, which then actually isn't that robust. It's going to blow up quite easily, as you will see. Okay, so far the finite difference part. I won't say anything else about implicit schemes. So you can set up some advantages, disadvantages, but I would say as a quick conclusion, the explicit, easy, and actually force you to have small time steps, resolving the time development correctly anyway. Implicit schemes, the only good thing is that yes, you can take big time steps, but then that implies big adder, and it implies a lot of computer work.
But is it a disadvantage to use implicit scheme with a very large time set to find the steady state solution compared to using another solver for finding the steady state solution?
It will actually be just equal. It will be the same job.
Yeah.
Remember, for finding the solution in one time step with an implicit scheme, you have to solve an equation system.
Yeah.
If you remove the time derivative from the equation, looking at just a steady state problem, you have to do exactly the same. So they are quite comparable. So when I say, yes, it's efficient finding the steady state in one step, but that's exactly as you say. Just remove the time derivative and solve it as a steady state problem. It's exactly the same. So, yes. Other questions? Yep.
Can we use modified equations for the numerical calculations, or only to stability and resistance check?
You can always set up or try to set up the modified equation. It will not be funny to do it with a fully implicit scheme, but I think it's possible. I never tried it. It's going to involve a lot of algebra. So fire up Maple. Maple is very strong there. You can insert a Taylor series with n terms. Very easy. So Maple is a very strong tool. So that one is really something you should look into. So if you do it, tell me. I would be interested, but I don't have time myself, so I won't do it. But feel free. That could be a nice 1A question on the exam. Yeah, next time I will start then looking into this finite volume, old theory by Patankar, and also then I will have a peek into the first chapters of this book by Verziger quite quickly, but I want to show you these examples that are here. It's not many of them, but they are interesting, and we can learn something about it. Also, I love his conclusion. I think he said it here somewhere. Oops. First order upwind scheme is inaccurate and should not be used. I like it. But we'll see that next week. Remember then, next Wednesday we have to be in F4. Else we meet here Tuesday morning. Okay, let me stop here.